Meeting. It is my pleasure to introduce our plenary speaker, Dr. James, or Jim. We'll refer to him as Jim from here on out. Pawlczyk. Jim received his PhD degree from University of North Texas in 1989 in biology physiology. He completed a postdoctoral fellowship in cardiovascular neurophysiology at the University of Texas Southwestern Medical Center in and around 89 to 92. And since 1995, Jim has been an associate professor of physiology and kinesiology at Penn State University in University Park, Pennsylvania. I had the opportunity to visit with Jim and the students at the Knoll Labs several times when I was at Penn State College of Medicine in Hershey, Pennsylvania, about a couple hours south of there, back in 2000 to 2012, and was always impressed with the infrastructure they had, the environment, the training culture, how enthusiastic and engaged his students were. Jim has had an incredibly distinguished career with research experience and expertise that extends well beyond those of most career scientists, certainly any that I have known. And as a physiologist and kinesiologist by training, his research is focused on dynamic blood pressure regulation, how disuse atrophy affects the ability to regulate blood pressure. And as many of you know, this is routinely observed when folks return from spaceflight back to a gravity environment. Jim has both research and personal experience with this phenomena. In 1995, he was selected as a payload specialist for the NEROLAB space mission and took leave from Penn State University to fly aboard the STS-90 on Space Shuttle Columbia in April-May of 1998. In that mission, he logged 16 days, 6.4 million miles in space, and managed to circle the Earth about 256 times while he conducted various experiments that address the changes in development of the nervous system, balance, blood pressure regulation, sleep, and control of movement during spaceflight. He's testified before the United States Senate Subcommittee on Science and Space. He's an active member of NASA's Advisory Council and Research Subcommittee for Human Exploration, the National Research Council's Committee on Biological Physical Sciences and Space, and the Institute of Medicine's Committee on Aerospace Medicine and Extreme Environments. Please join with me in welcoming our plenary speaker, Jim Pawlczyk, who will discuss human limits to exploring Mars.
Harold, thank you very much for that warm introduction, and we miss you back here in central Pennsylvania. Hope you'll come visit us again sometime.
Be delighted.
Well, thanks again for everybody taking a time out of your summer to come and talk about one of my favorite topics, space. It has certainly been popular in the news these days. This is a very dynamic time in space exploration as we begin to expand our footprint in low Earth orbit, soon to be moving back to the lunar surface, and then ultimately in the next few decades onto the planet Mars with a human landing. And so it's only appropriate that we include Fox's view of this with an image from The Martian. So I'll challenge all of you at the end, if we don't have questions to talk about, to name me some of the things that are wrong from a physiological perspective in the movie The Martian. So I'm going to do this as a combination of a physiology talk and an astronaut talk. So if you do an astronaut talk, the first thing you have to do is to show views of the Earth, because everybody likes to see that. So just to orient ourselves, so of course brown is dirt and green is vegetation and blue is water and white is clouds. And would anybody possibly know what place on the planet this might be? And hearing none, that doesn't surprise me because it's a pretty nondescript part of the Earth. But the clue should be the clouds, because of course they are usually what are sitting over our university, which is right here. So this is the home of Penn State. This is State College, Pennsylvania. This is a local mountain, Mount Nittany. going down to visit Harold or Harold visiting us, he took this route right here. This is US 322. And ultimately we crossed the river right down here. And then this is the Harrisburg area over here. And this river that you see right here, this is the west branch of the Susquehanna River. But I think maybe the view that we really want to be looking at, or at least thinking about, is this one. And so my challenge or my question for the group today is, what is it that it will take for us as a society to actually put boots on the ground and to be visiting and ultimately staying for long periods of time on the planet Mars? So it's not that far-fetched to me. Because when I think about Mars today, and this is what Mars looks like, and certainly you see that we are, yes, leaving a human impact on Mars on a regular basis. This also disappears on a regular basis. This is the Dingo Cap crater in Dune. But if you think about us during the 21st century as a society, we've always had humans in space during the 21st century. And we are now entering our third decade on the International Space Station. Think about that. And we've always been at the planet Mars. So we have had a series of robotic missions that have been on Mars for 2 decades. We are doing high resolution mapping of the Martian surface that has enabled us to look at the dynamic state that Mars is in right now and how it is changing, and also to scout out interesting places for future human landing on the planet. Now, we will get there through something that NASA has referred to as M&Ms, and that is really thinking about the Moon to Mars strategy. So we are in this phase of it right now with the International Space Station. We will be shortly moving into the vicinity of the moon. One of the key things that'll be really interesting as we return to the moon is that we will be establishing a habitable gateway that will sit in a high rectilinear cislunar orbit. And that gateway could also be used to then send additional vehicles off for planetary exploration. So it looks very different from the type of exploration that we did back in the 1960s for the lunar surface. And again, we expect that we'll be out in the 2030s or 2040s by the time we're actually returning to or moving on to the Martian surface. Now, in order to do so, we're going to need big vehicles. And this is kind of an interesting slide for me because this represents the evolution of spaceflight, and most of the vehicles here are not produced by NASA. And in fact, the vehicles that are flying here, there's only 2 of these vehicles that are flying right at the moment, and then the other ones are really imminent. So the vehicle over here is the Space Launch System. So this will have the capability of taking humans back to the lunar surface and beyond. That will probably be launching within the next 2 years or so. It's going through its full-scale integration right now. You can see that it uses derivatives of shuttle hardware, so the solid rocket boosters, the external tank, and in fact, the engines are derived from the Space Shuttle program. The Falcon rocket, this is Elon Musk's contribution to human spaceflight. You know, now is flying humans to the International Space Station. So has done so twice successfully at this point and is becoming part of the regular flight repertoire. And more evolved versions of this are capable of carrying even heavier cargoes to low Earth orbit. That will soon be followed this summer, hopefully, by launches, human launches of a spacecraft developed by Blue Origin, so New Shepard, and then ultimately the New Glenn derivative. This is now being fabricated at a factory in Florida, and this will have a considerable capability as well for heavy launch capability. Not to be outdone by the New Space guys Old Space is doing their business. So Boeing has developed a craft, their Starliner, and that has the capability to be launched either on a SpaceX or on a Boeing rocket. Also launching on the United Launch Alliance or Boeing rocket will be a small cargo craft that is a bit of a space plane. So this is Sierra Nevada's Dream Chaser. And then we also have cargo capability going from Cygnus Orbital Sciences. And that is designed only as a cargo capability at this point. So lots of things happening, and maybe more than you're thinking about. And of course, this doesn't even mention what international partners are contributing. So phase 0 looks like now. We know that the International Space Station will be with us through 2024, probably through 2028, and even also pretty likely to 2030. And this is the way the International Space Station looks right now. So the International Space Station itself is the largest vehicle that we have ever put in low Earth orbit. We have about 450 metric tons and a habitable volume that's equivalent to approximately a standard US 3-bedroom house. With the solar arrays here, the entire surface area covered by the vehicle is equivalent to approximately a football field. It's orbiting the Earth every 90 minutes. And if you ever want to watch it, which I encourage you to do so, this is there's 2 different ways that I think are easy to do this. So you can go to the government site, Spot the Station, or if you're an Android person, this particular app, ISS Detector, is pretty nice. It will identify where you're located, tell you exactly when the space station is flying overhead and when you can view it. Don't be late for your space station watching party at the latitudes that you exist in central Michigan. You're probably looking at the longest passes of between 5 and 6 minutes. So definitely don't be late, but you'll see it as essentially what looks like a very bright star, a little bit fuzzy perhaps, and that moves across the night sky. Don't bring your telescopes, because the tracking systems on telescopes just aren't fast enough to keep up with it. It's moving at about 18,000 miles an hour. But if you bring some field glasses that are pretty good, you might be able, and you have good eyes, you might be able to pick out actually a little bit of the structure of the solar arrays, which is pretty cool to see. Now, on board the space station, we have quite a bit of capability for physiology. So we can do this both in a human way or in a non-human way. So some of the human measurements that we have available to us are things that certainly are familiar to you for those of you that maybe work in human physiology or kinesiology. Those of you that work more in the non-human realm, we certainly have culture capabilities. We can crystallize. We've got housing for a number of different research animals as well. And we do have some capability for systems biology, and this only continues to grow. So the steps that we're looking at to move on to Mars, once we go beyond the International Space Station, we'll plan to be landing at the lunar South Pole and to place the first woman and the next man in this area. Hopefully by 2024, right now it's looking more like 2025. This will be very different than what we see with Apollo. So in the early phases, it'll only be a couple days on the surface. By the end of the decade, will be several months on the lunar surface. And also establishing this gateway that will allow us then to essentially think of this as a taxi service, sort of a local train, if you will, to this node, the gateway that will be orbiting close to the moon. We can then from there dock other vehicles that will be more like our long distance train. And that's the deep space transport capability that will be happening in the 2030s. So using the gateway, we will essentially transfer to the gateway, transfer to our deep space transport, and from there go on to Mars. So how we get to Mars, it's up for debate a little bit right now. In particular, one of the key things is the form of propulsion that we will use. We will use chemical propulsion, nuclear propulsion. It's all on the table right now. But what is key about the way that we will go to Mars is we will use a strategy that is different from what we've ever done in human spaceflight. And we're learning how to do it right now. And that is the idea of using the resources of the Martian environment to land us there and keep us healthy and safe there, and actually to get us back home. So in situ resource utilization, or ISRU. The first thing we can use is the fact that Mars has an atmosphere. It's not a great atmosphere, and we'll talk about it more in a few minutes, but the Martian atmosphere presents for us an opportunity to create some drag on a vehicle, so we can actually use this to slow down a vehicle and to capture us into a Martian orbit. So the idea of aerobraking, we've not been able to do that before, and we're starting to get pretty good at it. Ultimately, we're looking at a crew of approximately 4 to 6 people that we would be putting on the lunar surface, and we entirely expect that that will be an international crew. So let's look at the general plan on what it might take to send one of those human missions to Mars. Now, the way that orbital mechanics works is that you've got Mars pretty far out, Earth pretty far out, and what we need to do is to look for moments of alignment when it's energetically favorable to move from Earth orbit out to a Martian orbit. And those opportunities happen about every 2 years. So we're looking at approximately a 2-year cadence for these flights. So I've given you one example here. So in 2014, in January, if we had had an Earth departure at that point, the outbound trajectory to Mars would have taken approximately 6 months. Now, at this point, you have a decision to make. You can stay on the Martian surface for about 30 days, and it still remains energetically favorable enough to leave the Martian surface and return back to Earth. The orbital mechanics work. The alternative to that is to say, well, what if we stayed on the Martian surface for about 1.5 years? That creates a new opportunity. And so departing then on January, in this case of 2016, in about 6 months back. And that gives us an opportunity for all kinds of science. And this, in fact, is our Mars Design Reference Mission, which was so well represented in the movie The Martian. So if you look at this, about 2.5 years off of the surface of this planet. And so that presents a really interesting challenge for us. And let me explain it in this way. We have been a spacefaring society, I mean worldwide now, for 60 years. So this year we celebrated Yuri Gagarin's flight into low Earth orbit. So if we think about the duration of a mission in the distance from the planet Earth, this is kind of the things that we know. So we look at the distinguishing line, the von Karman line between the atmosphere and space as 100 kilometers or 62 miles. So we have several vehicles that are doing this on a regular basis, but suborbitally. So Blue Origin is very good at this, and they'll be launching, again, regular paying customers. So you will be able to go as a tourist. Virgin Galactic has been doing this as well. The ISS sits at an altitude of about 250 miles, give or take, depending on where we're actually at in the orbital cycle. Our duration is usually about 6 to 12 months. And the furthest we've been has been to the moon, which is about 240,000 miles. But of course, so that's sort of our known limits of life beyond Earth. Now, if we start to think about Mars, we're talking about something approaching 3 years and many, many more millions of miles from Earth. And if we think about some asteroids, which are reasonable to visit, we're also talking about probably a very long mission and many millions of miles this way. So that really represents to us the great unknown. So our challenge is to extend our operating envelope from these known limits to what it will take to go to Mars. And we're working on that, but we still have a long ways to go. Now, what I've done in this slide is I've summarized for you the entire human long duration spaceflight experience. At this point in time, we've had 500 and some odd people who have actually gone to space. I think I was number 338 amongst that. Some people have gone multiple times, so the total number of space forays, if you will, approaches about 1,000. And this is considering not just the United States, but all other spacefaring countries. And what I've done is I have restricted this slide to those people who have had an instance in space of 30 days or more. So I've actually removed myself from my own slide because at 16 days in space, I don't make it on the list. But those total number of instances in space right now are just shy of 290. And this is current and up to date. And we'll be adding a couple more data points to this slide by the end of the year. And what you'll note is that the bulk of these actually are from Russia or the former Soviet Union. And on the American side and our American partners, considerably less than that. So basically what happened was we had a space race going on going to the moon. The Russians built a lunar rocket. They had too small an engine that created all kinds of engineering challenges for them. And 4 of their lunar rockets failed. And at that point, they kind of threw in the towel and they said, we're going to focus on space stations. And throughout the 1970s and 80s and 90s, Soviet Union and Russia had a phenomenally successful space station program, the Salyut series, and ultimately culminating in the Russian space station Mir. We had just a brief little toe in the water with that with Skylab back in the 1970s. Most of our experience comes from the International Space Station and some from collaboration with the Russians in the 1990s. And you'll notice that most of the times our forays on the International Space Station have been limited to 6 months. But we have gone longer than that now. So we are starting to extend out to a year. So most of you are familiar with Scott Kelly and his year in space. And in fact, he is right there. He did not make it the year in space. It was actually about 11 months and change, but we're not going to quibble about that. The more long duration experience has happened actually on the Russian side. So they've had a total of 4 people who have made it beyond a year. And there is one lone soul here. You can barely see it. It's close to the pixel resolution of the screen. That is Valery Polyakov. He's a Russian cosmonaut and physician who flew on Mir in 1995 and 1996, flew for a total of about 15 months. And he actually had to negotiate his landing rights in Kazakhstan because that was the time when the Soviet Union broke up into its Commonwealth independent states. So, but that's still far short of the 30 months or more we were saying to be on the Martian surface. So part of our challenge then is to really expand our understanding of physiology, especially human physiology, from this 6 to 8 month realm out to the 3-year period. So what are the things that we worry about when we start to talk about exploration class space missions? Well, there's a few things that we consider. And if you think about what is unique, the things that are unique when in planetary exploration are really these 5. It's the fact that we're in a different gravitational field, that we spend all of our time in a can. There is a radiation environment that is completely different from what we experience here on Earth. We are isolated and confined And imagine yourself standing on the Martian surface, and that's what Earth would look like. Much, much smaller than the pale blue dot that Carl Sagan described. So that profound sense of isolation that would result from that is indeed a big challenge. Phoning home, it's 20 minutes to get a message back to Earth. But our human physiological challenges, I would sort of break down amongst many different systems. And I'm only going to focus on the two that are highlighted here, the environmental challenges, and I'm going to focus a little bit on bone. But each of these could be a long discussion in itself. So what does the Martian environment look like? Well, I've laid out 4 key parameters here, and Earth being shown in green, Mars being shown in red. So as I've mentioned, Mars has a different gravitational field that is smaller than our planet. So we are 1G here on planet Earth. On Mars, we're about 3/8 of that amount. So much, much less. That's both a good thing, and that is also a challenge, or that is also a challenge to us. If you just think about temperature, if you think about planet Earth, and we come up with a global planetary average, so we average over all seasons and over all latitudes, we are looking at something on the order of about 16 to 17 degrees C. If you look at this on the planet Mars, average global temperature on the planet Mars is less than -60 C. And if maybe you're more of a Fahrenheitist and aren't really comfortable with what -60 C means, remember that the Fahrenheit and Celsius scales cross or converge at -40. So -60 C, I think we would agree, is pretty freaking cold. Now, I mentioned that Mars does have an atmosphere, and of course, we measure atmospheres in bars or millibars. So at sea level, we're 1,000 millibar. And I didn't forget to put it here for Mars. It is there. It's just barely at the pixel resolution again of our screens. But that air pressure on Mars is about 5 millibar. So it's a very, very thin atmosphere. And its composition is completely different to that on Earth. So here, of course, we know we are 21% approximately oxygen, and then 79% inert, so mostly nitrogen and a little bit of argon. If we're looking on Mars, 95% carbon dioxide. So being in central Michigan, maybe you're familiar a little bit, farming communities, the idea of silo gas. So when you accumulate large amounts of CO2, it is absolutely toxic. But CO2 also presents for us an opportunity. And so remember, what we're going to do is we're going to try to use the resources of Mars. And one of the resources that we're going to go for, not just the CO2, but we're also going to go for the water. So to make it very clear, at this point, we know that there is water on Mars. We used to believe that it was not very accessible. It turns out that it is quite accessible. So our belief maybe 10 or 15 years ago came from things like this as the Mars Global Surveyor. And here focusing in on this rim of this particular crater, this is the blow up that you see over here. And you see areas like this, these slumps. And certainly that would look like anything that we might imagine for a small canyon or reentrant that we could find anywhere on this globe. And we used to believe that these were relatively young in geologic time, that maybe they had been formed within the past 10,000 years or so. What we now know is that these kinds of features are being formed on a regular basis on planet Mars. And what happens, we believe, is that on the rims of these craters, the angle of incidence is such that they get quite a bit of solar radiation. It melts a little bit of subsurface ice, and that as that turns to liquid, it forms this slump. And we can see these features form because we have this continuous presence around Mars. So let me show you some of the things that happen. So here's another from MRO, from Mars Reconnaissance Orbiter, that is surveying the planet. So this particular crater is pretty small, right? So it's only about 30 feet across or so, and it's only about 4 feet deep. Pretty fine feature. And just after it formed, look at all of this ice that exists around the crater. Surveying that same feature just a few months later, where has all the ice gone? Well, there's a pretty simple answer to that if you think about it just in terms of physical properties. So we know that the 3 states of matter are solid, liquid, and gas, right? So typically, when we look at things that are moved from solid to liquid, they are melting. If they go from liquid back to solid, they are freezing. And of course, we have boiling or vaporization and condensation. What we sometimes forget about is that it is possible to move directly from the solid to gaseous state, sublimation and deposition, and that only occurs under conditions of low temperature and low pressure, exactly like what we see on the Martian surface. So what happens is that when these areas of ice are exposed, they sublimate relatively quickly in the cold temperatures in low pressures. Where do they end up coalescing? Places like this, in cold traps. This is the Korolev crater. And this is shown actually pretty close to the way it looks, quite a spectacular sight. I'd certainly love to be standing on the rim of that crater. Or in the polar regions. The only thing that is false about this particular image is that the vertical axis has been expanded by a factor of 3, excuse me, to show some of these geological features. So you can see that there is quite a bit of water ice, and this is also dry ice, so frozen carbon dioxide. So here's the opportunity that we have. We know that there's water there, and we could electrolyze that water, and we could make hydrogen and oxygen. We could then take that hydrogen, combine it with CO2 harvested from the atmosphere or from frozen CO2, and we could make this. We could make methane. And the byproduct, of course, is water. So if you think about this, what we have are in situ resources from Mars, water and carbon dioxide, and we can make breathable oxygen, potable water, and a fuel, methane. And it's a pretty decent rocket fuel. It's not super elegant, but it works, and it can also run combustion engines. So we've got quite a bit of resources here, and all we need is the energy to harvest it. So we will probably be flying small forms of nuclear reactors. Solar doesn't work particularly efficiently on Mars just because the photons are a little less frequent from the sun than what we see here on planet Earth. So in order to make this work, we'll probably bring a little nuclear energy with us. But now we're literally harvesting our oxygen from the Martian surface. But we do have some challenges. So some of the features that we see on Mars, these are what dust storms look like on Mars. So here in 2018, that's Mars. And then a couple days later, this is Mars covered in dust storms. And this went on for about 3 months or so. This is actually the dust storm that killed the Opportunity rover. So that's what it looks like. So you can see these stacked images as we went through during the summer, and it just literally blots out the sun. We also have smaller weather features. So these are dust devils that run across the planet. These actually end up being pretty handy because when our rovers encounter them, what they do is they fan some of the dust off of the solar arrays, and it raises the solar efficiency, brings it back to a more normal level. So we're already using the Martian atmosphere to keep our exploration going. But certainly we will need some capability to protect ourselves from the Martian environment. So that will likely be some form of inflatable structure. And you go, inflatable, how could that possibly be? You know, for more than a decade, we've already had inflatable spacecraft that have been orbiting the planet Earth. And we now have an inflatable module attached to the International Space Station as well. So we're doing these kinds of things already in preparation for planets. But what about some of these human challenges? And the one I'm going to focus on here is osteoporosis. So most of you probably recognize trabecular bone. So this is that spongy bone or lacy bone that we see in areas like the vertebrae. We see it in the areas like the iliac crest. And this is healthy trabecular bone over here, the beautiful, these kind of bone formation along the lines of force. And over on this side here, this is sick bone. This is osteoporotic bone. So you see the trabeculae are thinned. In some cases, they're broken. And in some areas, they're just completely absent. And without doing too deep a dive on bone biology, let's just say as we understand it today, we can remodel bone that we can thicken and thin trabeculae, but once they are lost, they don't return. So there is a reversible nature to bone loss and an irreversible nature to bone loss. The problem is that spaceflight also accelerates bone loss. So you might be familiar with this vehicle. This was our first space station. This was Skylab. So the original Apollo series of missions was planned out through Apollo 20. The Apollo series was canceled by Congress after Apollo 17. So the last 3 missions were canceled. The reason being that everybody felt it was boring to continue to go to the moon, if you can believe that. And so this flight hardware that was already built was repurposed as a space station, Skylab. The reason I bring this up, because there's a really interesting set of physiology that comes from Skylab. So this represents a study that was published a number of years ago by Scott Smith at Johnson Space Center. And what he did was he took advantage of the fact that in the late 1990s, we recognized a number of urinary markers of collagen cross-linking, so the telopeptides. Scott is also the curator of all urine and fecal samples that have been collected in space. And these intrepid souls, wonderful research volunteers on the Skylab series, actually collected a sample of every urine and fecal event on the Skylab throughout the duration of their entire mission. Those are curated and maintained at JSC. So once the N-telopeptides assays were available, Scott thawed out the urine samples, assayed them for N-telopeptide, and here's what he found. He found that telopeptide was increasing, representing an increasing rate of bone loss, and then it plateaued over this 12-week mission. So plateauing should be a good thing, but in this case, it's a very bad thing. What it means is that we had an accelerating rate of bone loss that was maintained over the duration of the flight. And ultimately, that translates to measurable losses in bone mineral. So using just standard DEXA scanning, and this has been done several different times, what we see when we look at astronauts in flight is that there's substantial bone remodeling. So if you look at areas like the skull, there's actually an accretion of bone. So if you've heard that astronauts come back thick-headed, it's true, it's in the data. But then if we look in the gravitationally dependent regions, the lumbar spine, the femoral neck, look at these rates of loss, 1.6% per month. And to put that in context, a US postmenopausal woman loses bone from this region at the rate of about 1% per year. So these are rates of osteoporosis 10 to 15 times greater than postmenopausal women in the US. So if you take that rate of bone demineralization, project it over our 30-month mission, this is what you might expect to see at the femoral neck. Nearly 50% of bone mineral would go missing. And just as a sanity check, you go, could that really happen? Is that physiologically plausible? Well, in this particular study, we looked at just a cross-sectional comparison of people who had chronic spinal cord injury for a duration of about 8 years. And compared to ambulatory controls, they're in the same ballpark. So people who are chronically unloaded. So also to put it in context, if we just put this up against the age norms, this means that if we're right, that people would be returning from Mars with a bone mineral density of an average US 100-year-old. Well, that's a little bit disconcerting because we know as bone mineral goes down, that fracture risk goes up. However, there's an interaction there, and the interaction is with age. So younger people, actually, at low bone mineral densities, their fracture risk does not increase that much. It's older people where you see this dramatic increase in fracture risk. Why is that? Because older people are more likely to fall. So there's a vestibular interaction. What we don't know is where astronauts would actually fall on the spectrum. Certainly there is disturbed vestibular function with altered gravitational fields, but we might just adjust to this by saying, you know what, when you land on Mars for the first week, we want you to stay inside, develop your Mars legs before you go outside, because we don't want you falling. So we know about bone loss. We haven't mitigated it successfully, but through operational differences, we might be able to control the risk. So ultimately, is this one of the ways we control the risk? Do we do it with exercise? And we have lots of capability for exercising on the International Space Station. So Ed Lu here is showing very nicely the cycle ergometer that exists. And no, you don't need a seat for a cycle ergometer when you're flying in free fall. Our treadmill, you do have to be tethered down to it, and resistance exercise devices. So here you see Nicole Stott showing off the 2 different versions of the treadmill. And we now have an advanced resistance exercise device. So here's Soichi Noguchi showing that in practice. Got to think about other aspects, though, of an exercise program. Many years ago, John Greenleaf did this calculation. He said, if we go to Mars, and in this case, looking at a 24-month mission, and of course, we're going to be working at an increased metabolic rate. That means we're going to have a greater food requirement, a greater water requirement, and a greater oxygen requirement. So if we were to exercise for 30 minutes 3 times a week, or for 60 minutes 3 times a week, how much extra consumables would you require to support the exercise program? And if you add all this up, it's close to 6 tons of consumable supplies. And remember, it costs right now to take things to space about $10,000 a kilogram. So what we have here is the most expensive gym membership that has ever been created. And certainly it speaks to the need for in situ resource utilization. If we can harvest this from the Martian surface rather than bringing it with us, the cost goes down dramatically. So ultimately, if astronauts went to Mars today, we would expect everybody would lose some bone mineral. Some would lose it pretty profoundly. Most would have a large loss in exercise capacity, at least as measured by maximal oxygen uptake. And many too would have a large loss in muscle strength. And I would submit to any engineer, if I told you that over this time in Mars that your system was going to degrade by 30% or more, that you would be pretty upset with that. Certainly we should be upset with that for the human system as well. And that's why we need to focus on physiology and physiological explanations and solutions for some of these challenges. So what do we need for spaceflight? Well, we've got to pick the right place, and we've got to go where the water is. In looking at the poles, that's one of the reasons we're going to the lunar poles, because we have water there as well. We need to demonstrate those technologies that we can actually harvest the resources of the lunar surface and the Martian surface. And again, that's part of the Artemis program. We need to extend the stay time. from not just 6 months on the ISS to now a year on the ISS, and ultimately beyond that out to 3 years, and to protect from the hazards, and certainly to minimize the physiological risks, bone, cardiovascular adaptations, radiation, which is a biggie that we haven't even gotten into, and also the psychological stress. So with all of that, I will fly the flag of my university and leave you with these thoughts from the father of human spaceflight, Konstantin Tsiolkovsky, and open it up to questions from you. And thank you very much for your attention.
Thank you so much, Dr. Walczak. I know I can speak for everyone and say that that is beyond fascinating. And I'll let everyone just go ahead and put your questions in the chat, and I'll read them out for our speaker. I'm going to kick it off, and I'd like to ask you about I'm really fascinated about the harvesting of oxygen in water. And but then you also mentioned that the barometric pressure is so much lower. So even if we can produce our own oxygen, to get it to 21% of a very low barometric pressure would matter. So how does the pressure piece play into sort of ventilation?
Sure, it's pretty straightforward. So our vehicles, our modules will of course be pressurized. And our plan at this point is to pressurize at Earth ambient pressures. This has been a huge debate in the Artemis architecture. So if you remember back to the early days of Apollo, there was a tragic on the pad accident where Apollo was at the Apollo vehicle, the capsule was at a lower pressure but 100% oxygen atmosphere. There was a spark that occurred under one of the seats that resulted in a fire that killed the 3 crew members, 3 astronauts who were participating in that simulation. After that time, we've gone back to Earth ambient pressures. The only time we go to low pressures is when we go to extravehicular activity. And the reason for that is, that 15 pounds per square inch, if you're trying to move a suit that's pressurized to that level, that's extremely difficult. It's actually impossible. And so we pressurize to about 4.3 PSI in a typical EVA suit. We'll go a little bit higher than that. We'll probably go to 4.8, but that creates a flammability risk. So we'd like to keep the vehicles at Earth normal. There has been discussion to go a little bit less, maybe 10.4 PSI or 8.7 PSI. But if you do that again, you can do the partial pressure calculation. You have to kick up the oxygen concentration, and then you start to increase the flammability risk again. So we prefer to avoid that and to stay at Earth pressures inside our vehicles.
Thank you. Some questions from the group. So, of course, everyone's thanking you for all of this. This is wonderful. Besides hind limb elevation and tilted bed rest, what other methods on Earth help us study the effects of weightlessness?
Good question. So I'm glad that people mentioned those 2 models. So certainly a common model that is used in the animal world is the idea of tail suspension. So this was originally developed with rats, has now been moved into mouse models as well. And this can be either done by suspending the tail itself at the base of the tail, or to use a sling to suspend the animal. The idea is that unloading the hind limbs allows essentially the atrophy to occur in the hind limb muscles, and that by shifting the hind part of the body to be above the heart, that you mimic some of the fluid shifts as well. If you want to work with more reduced models, so in cell culture, we use freely rotating systems. And so we have cell cultures that are in a constant state of free fall, so they never experience gravitational force in one direction. That's pretty successful. You said at humans, we use the idea of bed rest, and this is bed rest with a 6-degree head down tilt, something we'll call a strict 6-degree head down tilt, which means that the person never lifts their head at all. That does a good job of mimicking the early time course of the cardiovascular and blood volume adaptations to spaceflight. Another method that can be used is to use immersion. And so that immersion can either be done wet, where you actually put a person in water and allow water pressure to cause some of those changes, or it can be done dry. If you imagine putting a plastic sheet over a body of water and then laying down and immersing yourself with the plastic sheet then as the barrier between you and the water, that does a pretty nice job as well. And then we have other simpler models that, for example, we'll go extreme environments. We can do that either underwater, or we do habitats at either of the poles. And we also use those to mimic some of the isolation as well. So isolation chambers.
Excellent, thank you. You showed that average Mars temperature, or you showed the average Mars temperature, but the location excuse me, I can't talk, but are the locations that the rovers are now located more temperate for humans?
So no, they're actually not. So those are pretty representative. And of course, because the Martian atmosphere is so thin, the temperature dynamics are really large. So you can, on a really warm day on Mars, actually get up into ranges that certainly are more what we would experience, say, in a very frigid, cold day in North Dakota. So there, you might be up in the maybe -20, -30 C range, but you can also experience much colder than that as well. So warm is still very cold by Earth terrestrial standards, and cold is extremely cold.
Gotcha. What about the influences of a lack of gravity on plasma volume? Also, more generally, how will the gravity on Mars influence human physiology that has adapted to space on the journey there?
Boy, two really excellent questions there. So there's a lot to unpack. So let's start with the plasma volume. So we see approximately in space about 15% smaller plasma volume. And the red blood cell mass also goes down as well. So typically then we have people returning with something approaching about 1 liter less total blood volume than what you might see on the ground. And that is a big contributor to these disorders of blood pressure regulation that we see after spaceflight. We can modify that. That's probably an appropriate adaptation for in-flight, because of the fact that the heart is somewhat enlarged and that more blood is returning to the heart. Having said that, the old traditional Gower-Henry reflex that this would inhibit ADH really doesn't appear to happen in a series of studies that were done largely based at UT Southwestern in the 1990s. In fact, we saw the result is really more that there's a negative water balance, that people just decrease their water intake for the first few days of flight, and as a result of that, adjust their blood volume. But we can have people expand their plasma volume and expand their blood volume immediately before they come back home. There's several different rehydration strategies that have been proposed. Some of them use hypertonic solutions, others look much more like what we would see in the sports world. And I think those are the more efficacious, quite frankly. The other question was, what about the fact that Mars has a gravitational field and will be perhaps in a free fall environment traveling to Mars and then go to 3/8 of a G? So I should make a note here that I made the assumption in all of the estimates that I showed you that 3/8 of a G has no impact on bone loading, and I treated it just like it was a zero gravity condition, a zero G condition. And that may or may not be correct. Problem is we just plain don't know. So we've never been able to have any mammalian species for a long time at a G level that is some fraction of Earth G. And I think one of the most essential programs that we could add to our upcoming lunar exploration program is to place a vivarium on the lunar surface where we would have animals from multiple life cycles. So we could certainly do that all the way up to and including mice And I think it creates a really unique opportunity for some tremendous systems biology work. So if we could identify potential genomic variants that are less resistant to some of those changes, or perhaps are more susceptible to them, potentially we could design some really good interventions that would help people that are going to be off the planet for longer periods of time, multiple years.
Excellent. There's another question in the chat related to that sort of journey to Mars, the 6-month journey. So can you comment on how exercise training protocols suitable for the International Space Station will have to be adapted for that journey?
Yeah, so the exercise equipment that I showed you for the International Space Station, one of the things you should have appreciated from that is that it's really big. And we won't be able to do that for our lunar expeditions, and we're still not sure how much we'll be able to do it for Martian expeditions. But let's assume that we're always going to be power constrained and we're going to be volume constrained. So a big device is not the kind of thing we would want to fly. We would want something much smaller. So we're seeing a shift more and more in exercise training for astronauts in flight, away from traditional cardiorespiratory endurance training, more towards resistance exercise training. And there's a lot of good reasons to suggest that maybe something in between that, high intensity forms of interval training, are really the smart way to go. There was actually some clues to that back in the 1980s and 1990s by Vic Convertino, who showed that you could get some pretty quick improvements in plasma volume using high intensity interval training. When we do a little bit more RNA-seqs and see some of the changes that we're observing for animals in flight, one of the big areas that we see adapt are really looking at pathways of mitochondrial biogenesis. And we know that high intensity interval training is a pretty good way to stimulate those pathways. So potentially for plasma volume expansion, for loading, and perhaps for metabolic adaptation, high intensity interval trainings are going to be the best form of exercise prescription for flight.
Awesome. Well, we just to keep us on schedule with the rest, I think we'll just end with one more sort of interesting question about the fact that you've been to space and none of us have. So our president wants to know, which is more unnerving, the feeling of launching into space or re-entry into Earth?
Well, boy, that's an interesting question. The fact that you're sitting on a vehicle that is probably the most complex machine that humankind has ever created, and all of it was supplied by the lowest bidder, that can be a little bit unnerving. It's also true that I have never worked with a more talented or dedicated group of individuals that are concentrate in the spaceflight domain. So you get this tremendous sense of just respect for work, and the ethos of spaceflight is everyone up and down the chain. And so that tends to assuage any of your fears about lowest bidder. Coming back home, people are more focused on the fact that you will be coming back home soon. And so I would say probably Ascent is the one that is more unnerving, but it is a big kick in the back. And it is a tremendous 8-minute ride upstairs.
Wow. Such fascinating stuff. We will all want to thank you so much for your time. Perhaps what I'll do is I'll forward these other questions for you, and you can either try and answer them in the chat if you have a few moments, or whatever it may be. But thank you all so much for coming. Thank you, Dr. Pawlczak, for just such a fantastic talk.